Speaker in afternoon, Professor Mike Zaletel from UC Berkeley, and his talk will be about the Intervalley coherence.
Great, thank you. It's a pleasure to be back at Princeton giving this lecture. So I've cheekily titled it Intervalley Coherence, a Theory of Everything. It's not really a theory of everything. I'll also explain why a lot of the time you shouldn't get intervalley coherence. But really, I'm using the idea of intervalley coherence, which is a type of spontaneous symmetry breaking relevant to a lot of 2D materials. For example, it shows up in magic angle graphene, trilayer magic angle graphene, rhombohedrally stacked graphene, I believe some of the TMD compounds. So it's become very prominent in all these interacting 2D systems looked at in the last couple of years. And I'm going to use, I'm going to use intervalley coherence as a vehicle for talking about the mean field theory approach to understanding the nature of symmetry breaking in all these 2D systems. That's Hartree-Fock. Hartree-Fock sounds very boring. Like if a state is described by Hartree-Fock, we sort of by definition say it's not correlated, even though it might be strongly interacting. But nevertheless, the structure of Hartree-Fock is actually quite interesting mathematically. And it's able to describe a lot of the phenomenology of these experiments. And most interesting to me, there's a relationship between Hartree-Fock and the energetics of various symmetry breaking states and quantum geometry like the Berry curvature. So really the point of this talk in a way is actually to introduce what is Hartree-Fock, how does it relate to quantum geometry, and IVC is just a vehicle for thinking about it. And what we'll see actually is that if you look at the long wavelength limit of Hartree-Fock, the energetics of a symmetry breaking state end up having a description as a sort of nonlinear sigma model in momentum space. And in the case of IVC, that's going to let us establish an analogy between intervalley coherence and superconductivity. And I think it's a very powerful way of thinking about it, which lets you reason without doing detailed calculations about when intervalley coherence is a desired form of symmetry breaking. And then if I get to it, hopefully in the second lecture, we'll do a little bit of an application of these ideas to rhombohedrally stacked graphene studied by Andrea Young's group. Okay, so and hopefully you guys will, this is informal and people will stop me throughout the lecture. Okay, so if we're talking about intervalley coherence, we first need to know what valley is, and this is a concept which is very familiar with graphene, though it occurs in other materials as well. We know graphene, you have a Brillouin zone, which is this hexagon here. And the interesting thing about the band structure is that if you look at the states near zero energy, it doesn't occur just around the gamma point. Instead, there's actually two disconnected pockets of low energy states at the K and the K prime points. So in other words, if I'm interested in the physics of the system within some small window of zero energy, the low energy states localize into these two separate pockets here, and we call those pockets valley. Note that the fact that you had a Dirac point itself was not important here. So if you look at the transition metal dichalcogenides, for example, it has a gap spectrum. It kind of looks like this. It's sort of like massive graphene, right? So gaps open. But nevertheless, if you ask what are the lowest energy states, there are two gapped pockets around K and K prime. So again, in the TMDs, you also have this valley degree of freedom. It happens in various materials without a hexagonal Brillouin zone. For example, aluminum arsenide also has two pockets, but the symmetry of it's different. Rather than being related by C6, they're related by C4. Anyway, so this is the general scenario in which valley degrees of freedom arise. Now, we'd like to be able to come up with a sort of continuum field theory description of such a system which has two valleys. And to do that, we're going to use a decomposition of the field operator into the part of the electron field supported in valley K and the part of the field supported in valley K prime. So in graphene, for example, I have a field operator which destroys an electron at sublattice A, where this A could run over the A or the B sublattice at position R within space. And what I'm going to do is imagine that this operator can be broken into two parts. The part of the operator which creates electrons near the K valley in sublattice A, R, plus the part that creates electrons near the K prime valley. And you see what I've done here. This is just a C number, whereas this is an operator. I've explicitly factored out the fast varying part of the wave function corresponding to having momentum K, so that I can think of this field operator as now slowly varying compared to the graphene lattice constant. So long as the physics is restricted within a narrow patch of K and K prime, I can then think of the only important part of this operator and this part as being a slow varying part. And the reason that's useful is that we can now apply a continuum description by replacing discrete differences with derivatives and so on to these. So I'm going to be able to develop a continuum field operator for these, even though at the microscopic scale, of course, the wave functions are varying very quickly within the unit cell because of this large momentum here. Okay? So that's the basic idea in all these valley systems for how we're going to derive a continuum limit. And what we get by having two valleys is rather than having a single field, we now have two fields, so it becomes like a two-component problem corresponding to the K and the K prime. So that's why valley is sometimes thought of as a pseudo-spin. It makes the low-energy description have this new emergent spin degree of freedom. Okay, any questions about that? Okay. So the interesting thing, so I now want to talk about the general structure of what the effective Hamiltonian is going to be for these fields. And the interesting thing that we're going to discover in the case of, say, graphene and TMDs is that even though microscopically the only symmetry you have in the problem is the discrete lattice translation by the Bravaud vectors, it's going to turn out that in graphene, there ends up being an emergent U1 symmetry corresponding to separate conservation of the particles in valley K and K prime. Okay, so we call that symmetry U1V, and I now want to derive why it should be there in graphene. So let's think about the general form of the Hamiltonian we might write down for the system here. Some H, we want it to describe really just the low energy physics, so maybe I should write it as H effective. Part of the Hamiltonian is only going to involve the field operators in valley K. Part of the Hamiltonian will only involve the field operators in K prime. And then there can be some part which involves both types of field operators, H, K, K prime. So this, for example, is probably familiar for most of you in the usual description of graphene. I guess I'll move over here. A lot of chalkboard to work with. If we're interested in just the low energy behavior, we could describe the physics within a single valley, for example, using the Dirac equation in the case of graphene. So I get a psi dagger K by sigma nobla psi K. Oops, sorry, this is R. Plus dots. Okay. Now, implicitly, what are these dot terms? They correspond to the fact that as you look at momenta farther and farther away from the K point, the Dirac dispersion is not linear. There's going to be KQ terms for so on and so forth. But I'll ignore those here, and we can just keep the linearized part of the dispersion here. So that's HK, and there'll also be interactions within HK I'll come back to shortly. Now, let's just think on general grounds based on the symmetries of the system. What could the general form of this term here be? And so when I look at this term here involving both, I could decompose it into the one-body type terms, the two-body type terms, the three-body type terms, et cetera. So I'll just go through those one at a time and ask on symmetry, what can the form of each of those be? So first, let's ask about the possible one-body terms. That we could have in HK prime. So let's say H1. And by definition, if it's a one-body term, it has to devolve just one creation operator and one destruction operator. And because it's an interaction of some form between the two valleys, of course, it would have to be something that mixes them like this. So if I was to draw a picture of it, we have one valley here and one valley here. And it's some type of term which takes an electron from one valley and hops it into the other valley, K prime. Now I'm being schematic here. There's of course a structure because these field operators also depend on position and sublattice. So these are joined together with some matrix in the position and sublattice space, but I'll just thinking about it more heuristically for now, so leave that implicit. Now intuitively we know that this sort of term can't be in the Hamiltonian because by definition boosting an electron from K to K prime carries lattice momentum, right? They're not at the same point in the Brillouin zone. So that carries lattice momentum and then is forbidden by symmetry. Let's think a little bit about what that lattice momentum is, K minus K prime, because it's going to play a role in our analysis of the 2 and 3 body terms. Okay, so let me draw the Brillouin zone again. This is K. This is K prime, or equivalently, this is K prime. An important fact to know, at least in the case of graphene, is if you look at this momentum difference, K minus K prime, it's actually a reciprocal vector divided by 3. One way we can see that is, let me make another copy of the Brillouin zone here. And this is K prime. If you move along this line here, you'll see that going from K to K prime is the same as going from gamma to K. And if you do it 1, 2, and then a third time there, you'd come back to a replica of the gamma point. Okay, so we know 3 of K minus K prime is G over 3. Okay, so that's why it's forbidden that this momentum difference is not itself a reciprocal vector. There's also another interesting relation, which is that if you do K plus K prime is a reciprocal vector. So you can see exactly that if you add this vector and add this vector, you come to this point here. And by definition, this G is a reciprocal vector. Okay, so since K minus K prime is not a reciprocal vector, it's a third of a reciprocal vector. It's going to be a forbidden. But there's a nice way to kind of formalize this in terms of the continuum description by thinking of the lattice translation as actually acting as an internal symmetry on the 2 spinor components. So what do I mean by that? Let's save this decomposition here. And then just ask, how does the translation T1 microscopically, how must it act on the field operators? So we know if I take the translation operator along Bravaud vector either 1 or 2, by definition, this takes the field operator psi of R and translates it 1 over 2. And then what I can do is take this rule for how translation acts and just substitute it into the decomposition of the field operator into the 2 valleys and infer from that how must translation act on the 2 field operators. And what you find is that, for example, T1 will take plus or minus, where this here denotes K versus K prime, A R, and map it to psi plus or minus A R minus A1, but then combined with a plus or minus 2 pi I over 3. Where does this phase come from? It comes from the fact that I included in the field operator the fast-moving part of the momentum. Okay? So this has a cool kind of interpretation. How does the translation operator act in the continuum description? Well, first, it does a translation of the field operator. And this part we can think of is just some small change in the field operator, because by definition, psi k is now a slow varying field. So this sort of thing you could approximate, for example, this discrete difference by a derivative and use the usual approximations. But this is a part which comes from the UV physics, the fact that there's a k and k prime. And what it means is you can kind of think of T1 as acting, this thing here, I could exactly rewrite as a phase e to the 2 pi I over 3 tau z, where tau z is going to be an operator which denotes that you're either in the plus or minus k valley. So the takeaway from this is that the T1 operator you can kind of think of as an internal symmetry acting on the two valleys, which acts as this 2 pi over 3 rotation in the pseudospin space. Okay, so that's the intuition I want to have. And interestingly, if you do T2, so this becomes equal to T1. If you do T2, you find you get the opposite relation, 2 pi over 3 tau z is equal to T2 with a minus sign here, such that T1 combined by T2 acts trivially, coming from the fact that, as we found, T1 plus T2 is going to produce a reciprocal vector when acting on k plus k prime. Okay, so then the picture in our field theory is that the discrete translations are going to embed themselves as this particular subgroup, as this particular group acting on the field operators. Okay, so with this rule, we can then go to analyze the possible interactions for the 2 and free body terms that could be in HK. So let's move on to the possible 2-body terms, K, interacting between them. They come in 2 sorts. One sort would be something that looks like this. It creates 2 electrons in the K valley and destroys 2 electrons in the K prime valley. And the other sort would instead be a scattering term, K prime, psi K, psi. So if I was to draw a picture of these 2 terms, this type of term takes 2 electrons and scatters them between the 2 valleys, whereas this type of term takes 1 electron, it scatters it within one valley and scatters it with another valley, but there's no net transfer of electrons from one valley to the other. So now we can ask, now that we know that T1 and T2 act as a 2 pi over 3 rotation on these fields, which of these is allowed? And if you look at this one, this will have this under T1, this will carry charge 2 pi over 3, this will be 2 pi over 3, and this will be negative 2 pi over 3 and negative 2 pi over 3. So overall, you get 4 times 2 pi over 3, which is not going to give you 1, so this one carries a net lattice momentum. This one, on the other hand, the charge of this is canceled by the charge of this, and the charge of this is canceled by the charge of this. So we know this sort of term is not allowed, while this term is allowed. Okay. So then we arrive at an interesting consequence of this. If you look at all the terms we've said are allowed up to the 2-body operation, it actually conserves the number of electrons in the K and the K prime valley separately. Okay? So what that means is that there's a kind of emergent, there's an emergent symmetry of this sort of Hamiltonian, which is that psi, which I can think of as being this spinor psi K prime, is going to have a symmetry not just by the discrete T1 and T2, but under a symmetry I'll call U1V, which takes psi to e to the I theta tau z over 2 psi for any parameter theta corresponding to the emergence of separate conservation in the K and the K prime valley. Okay, so the point of that is basically if you look at 2-body Hamiltonians in a graphene-like system, or anytime you have valleys at K and K prime and restrict to low energies, that Hamiltonian is going to have an emergent U1 symmetry, separate conservation of valley. Now, we know microscopically there's not actually valley conservation, so it's interesting to figure out what's the leading term which breaks it. We'd find that the leading term which breaks it is when you go up to a possible 3-body interaction. Now, microscopically, there's not a 3-body interaction, right? We have the Coulomb interaction, which is 2-body. But if you imagine that this effective Hamiltonian really comes from taking the UV model and then running the RG a little bit, during the RG, you're actually going to generate 3-body interactions out of the 2-body Coulomb interaction. And once we go to a 3-body interaction, we can finally find an Intervalley interaction which does transfer particles but preserves lattice momentum. And that would be a term of the following form. Psi, psi, psi. where you take 3 electrons from the K valley and then scatter them into the K prime valley. A term of that form. Now, in this case, because these fields all carry 2 pi over 3 under T1 and T2, but they all come with 3 of them, this is not going to have any net momentum. So this is symmetry allowed. So this sort of term has been analyzed, and what its magnitude would be by Aligner et al. Let me just give the reference. This is 0708 0394. And what they find is that the magnitude of this term, which is called the Umklapp term, is actually very small when you restrict your attention to low densities. So the magnitude of this term tends to go as the electron density Ne times the lattice constant squared. So it's about this much smaller than the typical two-body term. So as long as we're interested in these systems which are at low density, this sort of term is small. What does this term do to the U1 valley symmetry? Well, it breaks it down to a discrete Z3 symmetry. Because while this sort of term is no longer invariant under the continuous U1 rotations, it would be invariant when theta is equal to 2 pi over 3. Okay? So the basic picture is that in these graphene systems, there's some very small term at low density which breaks the continuous U1 down to a discrete Z3. So that term is there, but it looks like from various experiments that it's indeed small, because as I'll show you, there'll be lots of experiments where we'll see symmetry breaking, and the angle theta of the symmetry breaking will vary continuously in space, which tells us that the U1 valley is a decent symmetry. Yeah.
Just to clarify, A here is the microscopic.
Yeah. Yeah, it would be the graphene lattice constant. Yeah.
And I see. Okay, that's my question. Thanks.
Yeah. Yeah, it'd be the electron density away from neutrality. So in graphene, magic angle graphene, for example, there's a filling of on the order of 1 electron per moiré cell. So you could think of in magic angle graphene, the typical scale of this would be 1 over the moiré unit constant, because the density is on the order of 1 over the moiré constant squared times A squared. And in magic angle graphene, for example, the moiré constant is about 50 times the lattice constant. So you're at densities of about 1 over 50 squared. A similar calculation, for example, if you're looking at quantum Hall physics in graphene, instead of 1 over the moiré length, you do 1 over the magnetic length. And again, the magnetic length is typically, say, 10 nanometers. So again, you have a ratio of about 1 to 10, or 1 over 50, really. Likewise, in the ABC I'm going to be talking about, all of them, basically, this thing is about 1 over 50 squared. They all tend to happen at around the same density. Okay, so to good approximation, these systems have an emergent U1 valley symmetry. And whenever have a symmetry, we can ask whether, once we add interactions, the system might spontaneously break the symmetry. And if the symmetry which is spontaneously broken is U1V, we call that intervalley coherence. So intervalley coherence will be exactly a situation where the ground state develops some sort of vacuum expectation value, which mixes the two valleys, even though microscopically such a term is not allowed by U1V. Okay? And that's the definition of intervalley coherence. Okay, now I should mention another caveat about thinking of this as a continuous symmetry. So the one I mentioned is, strictly speaking, U1V is really a Z3 symmetry. But another is that if you think about disorder, which tends to be weak, but there is some disorder in graphene system, disorder will also break the U1 valley symmetry. Unlike charge, which really is a symmetry, and so can't be broken, disorder is a realistic perturbation, and it does break U1V. Let me just explain why that's the case. Let's imagine I have graphene. And sort of disorder that happens is sometimes one of the carbon atoms gets replaced by nitrogen, for example. So I can imagine a single atom gets replaced there. Now, the actual effect of this is a little bit complicated, but just to be heuristic, you can imagine that the extra charge coming from the ion here produces a potential U of R due to the impurity. And what I can do is decompose this potential into the part whose Fourier support is localized near Q is equal to 0. So I'll call that UR, plus the part plus the imparted purity potential, which I'll call U plus, whose support is near K. So what I mean by this decomposition, if you wanted to do it formally, you could take the impurity potential, Fourier transform it, and then keep the low Q part of the Fourier transform and put that all here, and put the part of the Fourier transform that occurs near K or K prime and put it in here, so that U0 and U plus you can both think of as slowly varying compared to the lattice constant, and the fast varying part has been brought out here. Okay. So why is that interesting? Well, the reason is that if you now go to compute the matrix elements for this impurity potential, this part here is slowly varying, so it will be valley diagonal. It will scatter an electron from K to K or K prime to K prime. But by definition, it doesn't carry enough momentum to scatter K to K prime. But this part of the impurity potential, which will generally be there because the impurity is small compared to the lattice constant, so it's going to be spread out in Fourier space. It will have support around K. This part will exactly cause a matrix element between the K and the K prime valleys. So this term here will generate a term like psi dagger K, psi K prime. And the coefficient of it, the phase that goes out here, will actually depend where the impurity is, like which unit cells it in. So what that means is when you add impurity, it adds this term which breaks the U1 valley explicitly, but the phase by which it does so will kind of randomly vary depending on where the impurity is. So you can think of the real physics of the system as in the clean limit, you have this U1V, but then when you have disorder, it kind of acts as a random field in the valley space, which can prefer some symmetry breaking. So to actually analyze experiments, this might be, this can be important. And probably the reason I'll show you, I'm going to show you pictures of intervalley coherence in STM. Probably ultimately the reason we're able to see it is because this disorder kind of pins the continuous symmetry breaking. Okay, so just something to be aware of. So now I want to think about physically, if I have an intervalley coherence of this type, what physically does it correspond to? It's some sort of symmetry breaking. It turns out it's going to be a charge density wave or a spin density wave or a current density wave, depending on the situation. But one thing we can infer without getting into the detailed physics of what sublattices are hybridizing or what the spatial dependence is what the unit cell of that symmetry breaking is. So let's write down, let's look at the lattice of a graphene-like system, TMD, whatever it is. This is my triangular unit cell. And we know by definition that when we have an intervalley coherent order parameter, let's just call this thing delta to be schematic. By definition, under T1, delta will go to delta e to the 2 pi I over 3. Whereas under T2, delta will go to delta e to the negative 2 pi over 3. And just from this simple fact here, we can figure out what the enlarged unit cell must look like. We know that if let's call this unit cell a 1 type, we know that if I translate by T1 and T2, these two phases cancel and you come back to itself. So we know this unit cell is the same as this unit cell. So it looks something like this one. But that leaves this unit cell here, which I'll call a 2 type, and this unit cell here, maybe I should do it in color. But anyway, 3 type, 2 type, 3 type. Okay. So in other words, what it does is it takes the original triangular lattice and breaks it up into 3 sublattices, 1, 2, and 3. So it triples the unit cell. So this sort of symmetry breaking is sometimes called a root 3 by root 3 reconstruction of the unit cell. So whatever order it is, it must be something that has the periodicity of this tripling of the unit cell. Now, the actual interpretation of it, whether it's spin density wave, charge density wave, current density wave, is going to depend actually on the detailed form of what components are hybridizing. So what do I mean by that? Well, if we go back to putting in all the indices which I've been suppressing, in graphene, for example, we have valley, which I'll write as plus or minus K. We have sublattice, which is equal to AB. And though I won't talk about it much, we also have a spin, which is up and down. And my field operators that I've been talking about really have all three of these indices. So when I talk about intervalley coherence, there's a possible structure, tau S, psi minus, tau prime, S prime, which is some matrix in the space of, sorry, this is not tau, sigma. So when we talk about intervalley coherence and say that an expectation value like this is not 0, it's not just a number, it's really a matrix in the space of sublattice and spin. And as I want to explain, depending on what that matrix structure is, like whether it's poly X versus poly Y, et cetera, that's what determines whether this reconstruction corresponds to a charge density wave, spin density wave, et cetera. So there's many types of IVC. And actually, in the various experiments where I say, oh, they all see IVC, it turns out some of them I think are spin density waves, some of them are charge density waves. There's even different types of charge density waves. So I think I want to do, for the purpose of this introduction to IVC, is just focus on one of the types of IVC, which is very important graphene, called the Kekulé distortion, or the Kekulé-O pattern. So why is this an important sort of distortion? So in the Kekulé-O pattern, it's a type of charge density wave. And the reason we can, the structure that we get from it being a charge density wave rather than a spin density wave, that occurs if whatever this coherence is diagonal in the spin space. So you only get coherence between the up electrons, and down and down. But then there could be a more general matrix here. So this tells us that it's occurs in either charge or current. So it can either be a charge density wave or something like a current density wave. If it's not spin. And what's interesting is to analyze what are the impacts on the spectrum if you add a symmetry breaking of this form to graphene. So let's go back to our continuum Hamiltonian, our description of graphene. We have this Dirac Hamiltonian, which if I write it out in this Pauli language is the familiar tau z sigma x dot kx plus sigma y dot ky. So this is our usual sigma dot k description of graphene. But for those of you who have worked it out, when you want to keep track of both the k and the k prime values, it turns out that the sign of the x term actually depends on which valley you're in. So I include that by putting the tau x and tau z here. So what I want to infer is that suppose there's a symmetry breaking of this form, heuristically or phenomenologically, how is it expected to change the dispersion here? And one way of thinking about that is whenever you have symmetry breaking with a particular order parameter, it becomes permissible for the effective description of it to have that order parameter in the Hamiltonian. So in other words, what I can do is thinking about this order parameter instead as a perturbation that I add to the Hamiltonian, which becomes allowed on symmetry grounds. And then I can ask, depending on the structure of the M there, what impact does it have on the Hamiltonian? And the Kekulé is a very special type. It's the unique type of intervalley coherence, which actually gaps out the Dirac equation. So what do I need to gap out the Dirac equation? If I write this coherence as a general matrix of cos theta tau x plus sine theta tau z times some matrix in the sublattice space, and then I imagine you add this term to the Hamiltonian, what are the types of delta which are going to open up a gap? Well, by definition, to open up a gap in the Dirac equation, you need to add a term which anti-commutes with both this term and this term. If you add a term which only anti-commutes with one but not the other, it actually doesn't open up a gap. It instead just splits, shifts the Dirac cones up and down, but it doesn't open up a gap. So then we can then ask, if I demand that delta is something which is the identity in the spin space and acts only on sublattice, what terms here anti-commute with both this and this? And the only option is delta equals sigma x. So this type of IVC then plays a kind of unique role for graphene. It's the type of IVC which opens up a gap in the effective Hamiltonian. So now what I want to do is analyze what is the nature microscopically of such an IVC when you choose intervalley coherence, which is intervalley coherence, which is off diagonal in sublattice between A and B because sigma x is off diagonal here. And I'll show some pictures of this just in a second, both in theory and experiment, what it looks like and why it's called the Kekulé. Okay, so focusing on this term, let's see if we can infer on symmetry grounds what the charge density wave must look like. So to do that, let's write down how the different symmetries in the problem act in the spinor space. So the time reversal is an anti-unitary symmetry which flips valley, so it acts as a 2-ax and then comes with complex conjugation. Spin doesn't really play an important role here, so I'm just going to consider the spinless time reversal symmetry, which leaves spin invariant and just changes the orbital degree of freedom. So that's one symmetry. Another symmetry is the C2 rotation. C2 rotation both exchanges valley and exchanges sublattice, so it takes this form here. And then finally, you can work out what the C3 rotation symmetry of graphene is. It has this kind of interesting form. Like this. I won't derive this, but going back to the type binding description of graphene, you can derive that this is how C3 acts on the two valley degrees of freedom. So then what we can do is take the order parameter of that general, of that Kekulé type there, and ask, how does the Kekulé order parameter change under T3, C2, and C3? And what you find just by conjugating the order parameter by those operators there is that under time reversal, the phase of the Kekulé is invariant. Under C2, the phase of the Kekulé is reflected, and under C3, the phase of the Kekulé is invariant. So what we know is that this Kekulé distortion, the Kekulé distortion, is some sort of charge density way or some sort of density modulation, which is invariant under time reversal, which means it must be a modulation of charge rather than current. So it is indeed a charge density wave. And it also must be invariant under C3. And if you think about it, that's actually a little bit puzzling when you think of graphene to come up with a charge density wave, which is invariant under C3. Why? Well, let's go back to the graphene lattice. We know the Kekulé pattern is something that's going to have a 3-site unit cell. I'll call this unit cell 1, unit cell 2, unit cell 3. The naive way I might try and write down a charge density wave is to imagine that there's some extra charge which accumulates on a particular site. So let's say in this charge density wave, maybe there's some extra charge plus. that occurs here. We learned that this particular symmetry breaking is invariant under C3. So once I know there's some excess charge on this site, I can apply say C3 about this point, and I learn that there's also extra charge under this and this, where all three of these have the same excess charge. But by definition, these two lattice sites are related by T1. So that would actually then correspond to a pattern which does not actually break T1 or T2 symmetry. So the point is there's actually no way to write down a charge density wave where the charge accumulates on sites which simultaneously conserves C3 but breaks T1 or T2. So then it's a little bit perplexing. We must have a charge density wave where the density doesn't accumulate on sites. So to understand it, we really need to go back to the continuum description of graphene. Of course, when we think about orbitals, the electrons are not really just delta functions that can only exist in A, B. Really, they exist spread out and over space according to the Vanier functions of graphene, right? There's some s orbital here. And so it's meaningful to ask microscopically, not just about the density centered on sites, but also say the density in any region of space. And what we're going to find is that this Kekulé pattern actually corresponds to charge accumulation centered on the bonds of graphene rather than the sites. And once we realize that we can think about the modulation on bonds rather than sites, we can write down a sort of pattern which respects the desired symmetries. And it will be something like this. There'll be some enhanced density, for example, centered on this bond here, and this bond here. And then it continues in a pattern like this. Okay, so going back to why this is a tripled unit cell, you'll see in this particular unit cell, there's a strong bond on the bottom. In this unit cell, there's a strong bond on the top. And in this unit cell, none of the bonds are strong. Instead, it's like a star coming outwards. Okay? So this exactly has that square root by square root 3 reconstruction. But I've constructed it such that you can see that it's C3 invariant about any point. But it does actually break C2 symmetry, because if this bond is strong, this bond's not. And that corresponds to the fact that the angle of the IVC is not actually invariant under C2. So you apply C2 to this pattern, and it corresponds to a different orientation of the symmetry break. Okay, so you might ask, though, is this like the only thing it can be? I've said this is consistent with symmetry, but it's maybe not clear. It has to be something like this benzene-like pattern. So it's useful to have a totally foolproof microscopic way of saying, suppose you measure an Intervalley coherence. What does it correspond to microscopically? And maybe this is tedious, but I think it's kind of interesting to understand how we see this within the tight binding model. And then I'll show you some theoretical results of the modeling and compare it with the experiment, and we'll see it ends up giving patterns very similar to what's seen in STM experiments. So let me just say at a high level how you would calculate really what the density pattern is. So let's go back to the meaning of what a tight binding model is. In a tight binding model, the field operator, which acts continuously in space, we decompose into Vanier orbitals. Sorry. Let's see. Right, so remember when we do tight binding model, really we have a continuous thing, but what we do is we take the so-called Vanier functions, for example, s orbital, p orbitals. Lambda depends on whether you're at the A or B sublattice, and then Ri labels which of the sites you are within the system. And then we write the field operator using this orthogonal transformation in terms of operators that we think is adding an electron to a particular site. Okay? So then when we want to ask about the density on a bond, going back to what the tight binding approximation really means allows us to do that. Because the density at a point n of r, I of r, we can then write out in this form. There'll be just two versions of this. So I'll get a psi prime on Rj. Okay. And so to figure out the density on a bond, this lets us relate expectation values in the tight binding model, these occur at discrete points, to the actual continuous charge distribution. So what term here is going to be important when we talk about the density on a bond? Well, let's zoom in on two nearest neighbor A and B sublattices. Let's say I have A here and a B here. These tight binding orbitals are not delta functions. They're actually spread out in space in some way. So schematically, I'll represent it something like this. This here is a phi A. And this here is a phi B. And while they're orthogonal, there still is actually some overlap in real space. And so what that means is when you go to calculate the expectation value, where I choose R to be here, then what it's going to do is extract from this exactly a term which is going to involve this being on the A lattice and this being on the B lattice. So some term that looks like A at Ri. This one is site I. This one's site J. Okay. So what that means is that when you have your tight binding model, if you look at an expectation value between the two sublattices, if this takes on an expectation value, it corresponds to some increase or decrease of the density on the overlap region between the two bonds. Okay, so in other words, coherence between A and B corresponds to a modulation of the bond. Okay, so that's why the off-diagonal expectation values between A and B correspond to modulation of the bond. And you can actually work out that if it's a sigma X type coherence, it corresponds to charge on the bond. If it's a sigma Y type coherence, it corresponds to a current between the two bonds. Okay, okay, so this is how we can read out from the tight binding model what the continuous charge distribution is. And then I'll just very heuristically say how I could theoretically then produce a picture. It's kind of tedious. Once you write out that the charge density looks like this, we take our tight binding operators, and then we substitute in the fact that each of these field operators has a component in the K and a component in the K prime valley. And then the part of this which is off diagonal will then correspond to a modulation at wave vector K minus K prime of the charge density wave. So I hope you can see that at this point, once you specify the Vanier functions, everything is totally well determined for how you could microscopically figure out the charge density. You put in here our ansatz for psi being psi k plus psi k prime, and then you evaluate those expectation values, and then you can read out, concretely without any ambiguity what the charge density wave is. So I've done that just for some ansatz of what the. Can you put the screen down? So here are some plots for graphene where I just heuristically assume that the Vanier functions are something like some Gaussian localized orbitals about either the A or B sublattice. And then I assume an expectation value of the Kekulé type and write it, and then work out what the resulting charge density wave is. And it depends on the angle, the complex phase of that expectation value. So these two plots here are showing what is the density of all the occupied states, or correspondingly, you could ask what's the density of the unoccupied states. For the moment, you can just focus on what the filled states are. And then what we can look at is what does the charge density wave look like as a function of the angle of the IVC. So as I've discussed, it exactly gives this particular pattern here of some stars and then some benzene type things. And I can play a movie of what happens as theta changes. And you can see you get a continuous evolution between the different patterns as a function of the continuous angle of the symmetry breaking. Now, if you look at it, what you'll notice is, for example, At 0 degrees, the star is on this particular lattice here. And you'll notice that when you go to 120 degrees, the location of the star shifts over by 1 unit cell. Let's see if we can see that. Oops. Okay, I can't actually pause it, but you could, well, I missed 120 by a little bit. You can see the star has now actually moved over to this unit cell, whereas previously it was this one. Right? So that's exactly what we expect. Because T1 and T2 act as a 2 pi over 3 rotation of this order parameter, that means that changing the order parameter by 2 pi over 3 should correspond to a translation by 1 unit cell of the pattern. And the cool thing about the emergent U1 is it allows you, the system, kind of continuously do that rather than just discretely. So the reason it's called the Kekulé O pattern is because when you're hit 180 degrees, you'll see it makes a bunch of O-type coherences. So that's why it had the name of Kekulé O, even though in general, like if you look at it here, it doesn't actually look like an O. Okay, so let's compare that to an experiment now. This is an experiment down at Princeton, actually. So the system that's being looked at here is graphene at charge neutrality. It turns out if you just look at graphene at charge neutrality, there is no spontaneous symmetry breaking. But there's various ways you can enhance the interactions to drive symmetry breaking. So for example, adding a moiré potential. Here, in this experiment, what was done to increase the interactions was actually to turn on a magnetic field. The magnetic field leads to Landau levels, which quench the kinetic energy, making the relative importance of the Coulomb energy more important. And what they find is that there's a critical magnetic field where all of a sudden, when they image the system using scanning tunneling microscopy, which exactly images the density of the system at the atomic scale, there's a critical magnetic field where all of a sudden they see this Kekulé pattern develop. And you'll see it has remarkable similarity to the simplest sort of model I wrote down of these alternating Benzie type rings. There's the stars there, and you can see it triples the unit cell. Now, is there evidence from an experiment like this that the U1 valley really is a continuous symmetry? Well, if you have continuous symmetry breaking, you might expect that when you image the order parameter, you'll see that the phase of the symmetry breaking could have some continuous gradations in it in order to follow, for example, the disorder that I talked about, which locally prefers to pin it in different directions. And that's exactly what they see. So this is data from the same experiment. Here I'm zooming out in a 30 nanometer by 30 nanometer region. You'll see that in any given region, say like region 5 here, you get this √3 by √3 enlargement of the unit cell. But if you look in different locations, you'll find that the details of the √3 by √3 look different. And you can analyze this actually as if the angle of the symmetry breaking is changing as a function of position. Okay. So there's a way we could then analyze that actually, and at each point in space, right here, we just extract what was the angle of the IVC, and you'll see that you get an angle which has some interesting texture and gradient. So this is kind of decent evidence that there must be pretty close to a continuous symmetry, because if you had very strong Z3 anisotropy, the energetics would prefer it to be at either angle 0, 2 pi over 3, or 4 pi over 3. And you might expect to see, for example, sharp domain walls between the different phases. But here you can see the phase just kind of continuously changes around, which must mean there's not really an energy penalty for being at one angle compared to another. So this is some indirect evidence for this U1 valley symmetry being something to take seriously. Yeah.
What's happening at the center?
Yeah, so what's happening at the center is there's actually an impurity here, like the one I talked about. So presumably, the paper is kind of exactly analyzing why the impurity prefers this particular texture. So I probably won't get into it here, but that thing's an impurity, which is like pinning the order parameter in a particular way. Yeah.
And can the local behavior of the order parameter be matched to the impurity, local impurity there?
Yeah, we're able to, the mechanism here is kind of interesting. It's a little bit different than what I talked about the impurity having a slow varying and a fast varying part. I probably don't have time to get into it here, but it turns out that you can show that there's, in this problem, the order parameter is not just U1, it's actually SO3. And you can show that this, in this particular system, this defect induces a skyrmion in the order parameter. And what's being shown here is the texture relating from that skyrmion. So, I mean, really, in this particular case, the order parameter really is a vector rather than just a phase. I'm showing only the phase part, but in the other parts of the paper, we also show the out of plane part, and you can see that there's a skyrmion there. Interesting. Okay, so here's another experimental example of intervalley coherence. In this case, it's in magic angle twisted bilayer graphene. I'm going to show the bilayer case and some experiments from Princeton, but there is equivalent results in magic angle trilayer graphene from Caltech. So just a super brief recap of magic angle graphene. We take two pieces of graphene, twist them relative to each other. And the important thing as far as intervalley coherence is concerned is that when you have the moiré potential, it takes the original graphene Brillouin zone and then folds it down into a tiny little Brillouin zone. This is, really the mini Brillouin zone is about 1/50th of the microscopic one because there's a 50-site unit cell, moiré unit cell. But the important thing is that the low energy physics still gets restricted to these two pockets, an area here, K, and an area prime, K prime here. And because the moiré potential is low wavelength, the moiré potential doesn't cause scattering from K to K prime. So we still approximately have a U1 valley symmetry of separate conservation of electrons at K and K prime. So in almost all the models people study of magic angle graphene, you also have this U1 valley symmetry, which people take seriously. The details aren't so important for us here, but you end up getting famously, when you go to the magic angle, you get 8 very flat bands. And what they found is that when you fill 2 of the 8 flat bands, so in this thing here, what's being varied on the x-axis is the electron density, or equivalently how many of the bands are being filled. And they find, this is a measurement of the resistivity, when you fill 2 of the 8 flat bands, an insulator emerges. And that insulator would not be allowed based on single particle considerations because there's degeneracies between the 8 bands. And then when you dope that insulator, superconductivity occurs. So it was a question, this was observed in 2019, I guess, at MIT. I don't know how many papers there are on magic angle graphene, how many theory papers, hundreds, thousands. And really all of it, a lot of it is an argument about what is the nature of this insulating state driven by the interactions. And I think most people thought that most likely it's some form of spontaneous symmetry breaking, but there were many arguments about what was the nature of the spontaneous symmetry breaking. Was it spontaneous spin polarization, valley polarization, et cetera? And only very recently, last year, was there an experiment which showed conclusively that the nature of this symmetry breaking is indeed intervalley coherence. So let's see what they see in the experiment. These are, again, I'm being partial to Princeton. These are results from Kevin Nuckel's and Ali Yazdani group using STM. This is a typical STM image. You'll note that the moiré unit cell is about 10 nanometers. And so you see this large scale variation going from the center there to something over here. That's the moiré unit cell that contains something like 10,000 atoms. But this is STM, so they can look at the actual electron density with the resolution of single atoms. And that's this short wavelength variation here is the actual graphene scale carbon lattice. Okay, so zooming out, just to be clear, zooming out, the modulation from here to here is the moiré periodicity. And we're looking at just one moiré unit cell where we can see the texture at the individual carbon atoms. And you'll notice here, for example, in the top left, that they see, it's a little hard to see on the screen here, but it's exactly making this Kekulé O type pattern. Okay. So that's very exciting. How do we know this is spontaneous symmetry breaking? Well, here's the sort of experiment they do. It's a little bit complicated, so I'll walk you through it. Using a gate, they can continuously change the electron density to move the filling from, say, filling 0 of the flat bands to 1 flat band to 2 flat bands. That's exactly the x-axis or the y-axis here. So the very top is when the flat bands are empty. The middle is when they fill 2 of 8 flat bands, and down here is when they fill 4 of 8 flat bands. What's being shown here is the tunneling density of states. So they bring the STM tip and they ask, what is the rate at which electrons are injected as a function of the bias between the tip and the sample? If the system's an insulator, a finite bias is required in order to inject electrons. Whereas if the system is a metal, then you'll see a current at 0 bias. What you'll see is that for filling between 0 and 2, there's finite tunneling right at 0 bias, indicating the system is some sort of metal. But right when you get to -2, where my cursor is, you'll see that the tunneling density of states actually drops, indicating now that there's a finite bias of a couple MeV required to inject electrons, which is exactly the correlated insulator state. And then what they do is they can go to different electron densities and take a two-dimensional image using the STM of what the charge density looks like. When they're at filling below 2, they see a charge pattern which has the usual symmetries of graphene. But then right when they get near -2, you see the unit cell triples and forms a Kekulé pattern. And quantitatively, they can just ask, what's the magnitude of the Kekulé component of the images? And it shows this dome-like feature here. There's a particular point where the Kekulé turns on its maximum at filling 2, and then it turns off. So that tells you that the Kekulé is there in a way that depends on density, meaning this really must be some sort of spontaneous symmetry breaking rather than an artifact of the substrate or something like that, because it depends on density. So you can then interpret, this point here where it turns on as the onset of this continuous symmetry breaking. So I think this was an exciting experiment that finally resolved what the nature of symmetry breaking in the correlated insulators is, at least at ±2. Okay, now it turns out that theory had actually been able to predict that this should occur. And so in the rest of the 2 lectures, I want to describe what that theory is. And for better or worse, it's lowly Hartree-Fock. So just the least correlated approach you can take to electrons, it turns out, is basically able to explain even somewhat quantitatively why IVC is the form of symmetry breaking here. Can you raise the... Okay, so it's a little bit embarrassing to give a lecture on Hartree-Fock, but it's not something I really learned about till I was a professor, so I guess it's not too lowly for you. And I think it has a nice kind of mathematical structure. So Hartree-Fock is best understood in terms of variational principle. So variational principles are powerful ways to think about lots of different approaches to many-body physics. For example, matrix product states in DMRG is ultimately a type of variational principle. And in general, what we're doing is we have a set of parameters, just some set of numbers, GI. And then the variational ansatz is a map from those parameters into the many-body Hilbert space. So you can then think of this as describing some manifold in the many-body Hilbert space with coordinates set by the parameters. Of course, to cover the whole Hilbert space, you need exponentially many of them. What makes it a variational ansatz is we're going to use far fewer parameters, so we won't be able to describe every state, but as long as that manifold gets near the ground state, we'll do a decent job of describing the physics. The variational principle then tells us that the true energy of the system is upper bounded by the minimum over all possible parameters of the expected energy of the ansatz. So you minimize energy within this manifold, and then if the ansatz was powerful enough, meaning your manifold came close to the true answer, then the resulting state at that minima will be a decent approximation to the ground state. This is exactly, for instance, what the DMRG algorithm is, where this map corresponds to the set of matrix product states. Now, matrix product states are a great variational manifold because there's actually, theoretical proof that as the size of the tensors become larger, that you get closer to the ground state exponentially quickly, or almost exponentially quickly, faster than any power law. So matrix product states, DMRG, is a controlled variational algorithm because as long as you use large enough tensors, eventually you get the right answer. Hartree-Fock is an uncontrolled type of variational approach because the type of states we're going to be looking at are very special. They're going to be Slater determinants. So that then gives, once we have the variational principle, gives a very succinct definition of what Hartree-Fock is. Hartree-Fock just chooses the variational manifold to be the set of all possible electron Slater determinants or fermion Slater determinants. So what do I mean by that? The state G is hypothesized to take the form of some number of occupied orbitals acting on the vacuum. So that's the definition of a Slater determinant state. Where as usual, whatever these orbitals are need to be orthogonal. Okay. So what is the variational degree of freedom? I'll spell this out in a little bit. It's what are the wave functions of the occupied orbitals? So that gives a set of parameters. I'll spell that out in just a second very explicitly. Those are the G's that are kind of hidden in this notation here. And then you optimize over all possible occupied orbitals, evaluate the energy, and then minimize that. And that's the Hartree-Fock approach. Okay, so I'm gonna now embark. I guess I have 5 more minutes before the end of this one. Yeah, this is gonna be a little bit technical, I suppose, especially for the end of a 3-week thing. But it turns out that the structure of the Hartree-Fock has a very cool relation to quantum geometry, such that there ends up being kind of a heuristic picture for how to minimize this energy in terms of a nonlinear sigma model in K-space. And so hopefully that's what I get at by the end of this. Okay, so let me spell out a little more what I mean by this problem of optimizing over single particle orbitals. Well, let's say my original Hamiltonian, H, takes the very general form. You can imagine it's a tight binding model, for example, of some single particle hoppings, V1, Ij, plus 1/2, 2, IJKL. Okay, where the IJKL are summed over. So in a tight binding model, for example, these indices I would run over the orbitals and spin. But you could also think of this as just an abstraction also of I could instead be the momentum of electrons, and these sum then become integrals, or I could correspond to the position in real space. The point is, it's just any decomposition of the single particle Hilbert space into these indices here. So generally, your Hamiltonian looks like this. And what I mean by the variational parameters is that I need to define an orthogonal change of basis, Ci, Ui alpha, C alpha. Okay, so given one basis here, I can always define another basis, the alpha basis, which is related by some single particle unitary transformation. Or equivalently, I can write this out as C dagger alpha is equal to psi dagger I U I alpha summed over I. Okay, so then what you can do is choose this new basis alpha, and then you occupy some number of the orbitals. So the variational parameters I'm talking about, the G, are exactly this unitary matrix here, which tells you what the wave functions of those orbitals are. So this unitary matrix you can think of as the variational parameters. Okay, and then you're optimizing over basically all possible bases. It turns out actually that this is kind of a redundant description of the problem because there's going to be different U which actually give the same Slater determinant. So there's a more convenient way to think about this problem, not in terms of the unitary U, but in terms of the projector onto occupied orbitals. And the key result which allows us to do this is an alternative description of Slater determinants in terms of Wick's theorem. So Wick's theorem is basically, it's kind of equivalent to a Slater determinant. So any Slater determinant obeys Wick's theorem and vice versa. So to remind you of what Wick's theorem is, suppose I compute a 2-particle expectation value which I will define to be P. The reason I call this P is that what you'll find actually is that this I'll show this in a second. P is actually a projector, so it obeys P squared is equal to P. So it's basically, if you diagonalize P, it has a set of zeros and ones, which just specify which orbitals are empty and which are filled. Okay, so in general, let me just consider this expectation value here. What Wick's theorem tells us is that any higher point function factorizes in terms of the 2-point function. So if I have some ijkl, if you evaluate this with respect to a Slater determinant, then this becomes a product of two types of contractions, which we denote like this. So the first one is I take the product of this expectation value and this expectation value, so that gives P kj, P li. Okay. And this one involves an interchange. You have to exchange two to reorder them, so you get a minus sign, and this one gives P k I P lj. Okay, I certainly won't prove that Slater determinants obey Wick's theorem, but it turns out to be equivalent definitions. So what that means is that we know that any expectation value with respect to a Slater determinant can be reduced to just knowing this particular two-particle correlator. So the nice way to do Hartree-Fock is not to keep track of U, but instead to just keep track of this correlation function P. And I can think of P as being the variational parameters rather than U, though it's subject to the constraint that P squared needs to be equal to P. I had a constraint in terms of U as well. That was U dagger U, so you have a constraint either way. Okay, so my variational parameters is now the space of single particle projectors. If you want to figure out the relation between the P's and U's, it's rather simple. I won't derive this, but you get Pij is exactly the sum over the occupied orbitals of U j alpha. Alpha I. So that's the relation between them. Okay, so what this means is that because the energy, the expected energy we need in the variational theorem just depends on the expectation value of the one-body part and the two-body part, and these expectation values depend only on P, the energy depends only on P. But interestingly, from this description here, we see that P is invariant under various different unitaries. In fact, if we say that there's m orbitals and n of them are occupied and m minus n are unoccupied, you'll see that the projector is invariant under any unitary transformation acting only within the occupied space divided by unitaries acting in the unoccupied space. So it means that the actual variational manifold you can think of as like um divided by this. Okay, so what I mean by that is that the unitary is m by m if there's n orbitals, but the projector is redundant under any unitary which exchanges occupied and unoccupied. Therefore, the actual variational space you can think of as this manifold modulo this one. And this is called the Grassmannian. So you can think of Hartree-Fock as then a optimization over this particular Grassmannian space. Okay. So I guess I'll stop there and continue after lunch. Any questions?